Okay, hey everyone, good morning. Just taking a few more minutes until it's 9, but for the moment, welcome back. Hope you're doing really good, and we're gonna get this lesson rolling in just a few. About it means that there's someone there. And so the energetic rituals to enter exposure to the mind that is trained. So much like you get trained in the mind is trained. So you can get your body. There's some experience. Hey Ether, how's it going? Just a couple of us for the moment. Still a few minutes till class. Hey, good morning. Just another minute and a half. Hope you guys aren't too affected by the fires and stuff. I know that it's definitely a big factor in the city of Orange and just kind of throughout Orange County. I know that the Orange campus has been closed again, even though not too many people, I suppose, were really going to campus because of the pandemic, but you know very well, I'm sure, about how the university is trying to make a push for some limited in-person instruction to resume. But I guess fate has just decided that this is not going to happen right now. So for better or worse, we're all back watching Zoom. or YouTube. Hey, Kelly. Okay, good to see you guys. Good morning. Welcome back, as always. So it's another key meeting today because today what we're doing is we're going to transition to yet another topic in the class. We have a few more, ready to go, and we've finished the last one. So let me just kind of give you guys a sense of the overall scope of where we're at. Starting the class, it was all philosophy of religion, arguments concerning the existence of God and objections to the arguments and so on. Then it was ethics. What is the best available theories of morality, right and wrong, good and bad, Mill, Kant. How do we apply these different ethical theories to the consideration of real moral dilemmas, like whether we have obligations to the global poor, or what our intuitions are about killing and letting die, as seen in the trolley problem. And then after the midterm, we've just now taken a look at epistemology, which is a topic that's dear to me. That's all about knowledge. What is knowledge? What's the right analysis of it? And what are the different component parts of it? We started by learning about the ancient Greek theory, which was kind of the widespread consensus view for a long time. And according to those Greeks, knowledge is a justified true belief, something that you think is true, that actually, by the way, is true. It matches reality. And then furthermore, that you have evidence to believe it. If all three conditions were satisfied, they claim that that's knowledge. And Socrates had this dialogue with Meno where he goes over that and he talks about why the additional element of justification is what makes knowledge more valuable than just having opinions that happen to be correct, but for which you have no justification. So yeah, like justification provides for the belief to stay with you. And he uses the metaphor of the statues of Daedalus, that they're more valuable if they're, attached to the ground by ropes, because the myth was that they would run away if you didn't do this. So in the same way, a true belief is great, but it's not liable to stay for very long unless it's somehow grounded and based in your belief system with evidence. That's justification. Okay, and then there was Gettier. Gettier showed that the classical Greek definition of knowledge seems to have some problems. So he presents us with these scenarios, sometimes called Gettier cases, named after him. And what they show basically is that you could still have a justified true belief and still not have knowledge. So in one version of a Gettier case, the classic first one, Smith and Jones are looking for a job. They're the finalists. Smith believes Jones will get it because the boss told him that. Smith believes that Jones has 10 coins in his pocket because he literally counted them. So he forms the belief that Jones gets the job and Jones has 10 coins. And then he deduces from that the man who gets the job has 10 coins in his pocket. And since he's justified in believing the first proposition, he's likewise justified in believing the second one because it's entailed by the first. Okay, well then the end of that story ends with the boss telling Smith, surprise, never mind, I'm actually hiring you. Contrary to what I said before, I'm not going to hire Jones, but I will hire you, so you're getting the job. And it just is a total random coincidence, but it also happens that Smith has 10 coins in his own pocket. So it turned out to be true then that the man who gets the job has 10 coins in his pocket, but Smith, we would not say, knew this statement, because after all, although he did have a belief in it and he was justified in believing it, and it turned out to be true, the connection between his evidence and the real factors that make the proposition true isn't there. So it seems like he just got it right by just random dumb luck. And that's not the way that knowledge is supposed to work. Okay, and then so after that last lecture was Descartes. Descartes' whole book, The Meditations, is based around one goal. Sorry, let me do something here. My cat is over there almost dangerously getting close to the power cable. I don't want to topple the computer over. Okay, so anyway, yeah, Descartes' Meditations. He's trying to discover what is certain, because in his view, if we're going to start building this big body of scientific knowledge that seems to be really growing rapidly in the time he lived, then we should try to surely put it on a firm foundation. Something at the bottom there has to be absolutely unshakably certain, so that everything that we place on that foundation is also secure. So he says, how do we find out what is certain? Use the method of doubt. The method of doubt says to assume that anything is false if it could possibly be doubted. And so it's like a very, he thinks, powerful tool for trying to reveal to us what it is that cannot be doubted. And when the method of doubt is being used, he starts by saying, well, everything you perceive with any of your five senses could be doubted, because basically you can't say whether you're in a dream right now or whether you're having a real experience. And if you don't know whether you're dreaming, then you're not in a position to say that your five senses are revealing to you the facts about the environment around you. So maybe it's a dream, and if that's so, then none of your five senses can be trusted with 100% confidence. So let's assume that they're all false. What about math? Well, he says maybe evil demon could even make those things false. So he doesn't think that that's certain either. And then ultimately, he gets to the second meditation where he says, actually, though, there is one thing that cannot be doubted. Does anyone remember what that point was? The one and only thing that can't be doubted, according to the method of doubt? It's sort of like related to a famous quotable quote of Descartes that maybe we remember or that you have heard. Just let me know that, yeah, well, you say our, which is plural, but whose existence really, Eva, is known for sure? Whose existence relative to you? Yeah, your existence, because everybody else, all bets are off. They could just be things you're dreaming, but for sure you are thinking and having an experience of, let's say, apparently having a lecture that you're viewing. And just the fact that you're having this experience, whether it's an illusion, whether it's certifiably real, it just shows that you're something that is conscious and thinks, but maybe everything else isn't real. Nonetheless, you exist because you're thinking. Like, that's impossible to doubt. It was self-contradictory to say, maybe I don't exist, because you just had that thought. So thinking verifies that you exist. I think, therefore I am. That's something that survives the method of doubt. And later on in the class, we will return to this point as we explore what he thinks else can be proven, even with the method of doubt. Okay, so now we move to another topic in the class, and so we're covering this new subject matter, another branch, another field of philosophy, and it's known as metaphysics. Okay, so metaphysics is yet another subject area of philosophy. Originally, the word just means to go beyond physics. That was first used by the ancient Greek Aristotle. But today, we just kind of think of it more in general terms as like a deep investigation of reality and what exists. Okay, so when we are doing metaphysics, we're pursuing this type of topic. We are asking questions about the nature of reality itself. Like, what is this reality? What are the ultimate core constituents of it? What is a physical object? What is, for example, what does it require for an object to endure over time? Like, take this interesting question. Here you are watching a lecture today at whatever age you are. But if you look at photos of yourself, like, I don't know, 15 years ago, you're a little toddler and you're much physically smaller in those pictures than you are now. But you're the same person. So how is it that one and the same person has completely different physical features? Maybe you've heard the fact that every cell in your body is completely replaced every, 7 years or so. And so therefore, you're not even physically the same object anymore that you were through the replacement of your cells over, let's say, a 10-year span. So how is it that you remain the same object? There's all kinds of deep questions about personal identity, about material constitution, free will. Do we have free will, or are we just determined to act as we do, like cogs in a big machine that we don't necessarily control? Another interesting question in metaphysics, and the one that I've chosen for us to focus on in this unit of the course, is the question of time. So we're going to now basically look at a few lectures on the interesting and fascinating topic of time. What is time? What is the current best theoretical understanding of time, the best scientific concept of time? And, how is the new understanding of time that we have since Albert Einstein different from the Newtonian ideas of time that existed and that were the dominant view before him? So we're going to, dig around and learn a little bit about time. And that's our new goal for the next few meetings. Time. One thing about time, okay, and the reason that I think it's interesting, among other reasons, is that it's something that we all are well aware of. We all live our lives according to the clock. You guys are watching this now because probably you set an alarm and you recognize that it starts at 9 and it ends at 9:50. You're aware of the details of your schedule in terms of time throughout a 24-hour period. But even in the bigger picture, you're aware of how old you are, how long you've been alive, how much more time you have to do various things. You're aware of the passage of time as it's happening. So we live with time. It's just an intimate and fundamental aspect of existence and of the human condition. But the thing that's a little trippy and weird is, well, once you start considering beneath the surface level, well, what is time though? And you try and ask these deeper questions about it, you start to recognize that it's actually very difficult to explain in any depth once you go beneath the surface. But we're going to try to get to that deeper understanding, and we're going to start off today by reading the work of a very famous scientist and philosopher, and that is Albert Einstein. Okay, so Albert Einstein lived from 1879 until 1955. He wrote a lot of interesting and very powerful work. He won, Nobel Prize in physics for his papers that he published in his early 20s on the electrodynamics of moving bodies, which is sometimes known as the special theory of relativity, and there's also the general theory of relativity. So these papers that he worked on and published when he was before 25 years old became like these revolutionary landmark physics papers that demonstrated a whole new revolutionary understanding of time and space. That was in 1908 that he first published these famous works that he's well known for. But in 1916, about 10 years later, he wanted to produce a book for a more wide audience, like a more just non-technical, popular audience, so that he could make these ideas a little bit more comprehensible to the average person. And that's what this selection that we're reading today comes from. It comes from his 1916 book, which is a great book, just called Relativity. So in 1916, he wrote this book called Relativity, which tries to bring down to earth a little bit some of the heady concepts of his theory of relativity, which, if you actually want to grapple with the detailed technical aspects of it, it takes pretty advanced knowledge of math and physics, but there's a non-technical explanation of it that most people can grasp, and that's what he presents in 1916. This little article in our textbook comes from that, and they've given it they've retitled it so that it's, something from their anthology. The editors took the liberty of adding a supplementary title. And so here's the title that we're looking at for today's reading in the book from page 455, Time and the Relativity of Simultaneity. Okay, so this is really just a little small part of his big book, Relativity. And this is not the original title. This is just the title of the snippet that's been selected from the editors of our textbook and placed in this anthology. Time and the Relativity of Simultaneity from 1916. But again, like I'm telling you, it's really just a part of his book, Relativity from 1916. Okay, so Albert Einstein, this is one person in our syllabus that I'm sure you've heard his name. It doesn't take a person who's deep into philosophy or science to have heard of the iconic name and person of Albert Einstein. He's almost like, I would argue, the stereotypical pop culture caricature of like the genius scientist, right? With like the big frizzy white hair and the glasses and the tweed rumpled jacket and all of that. So yeah, Einstein is kind of like an icon in Western culture and known as like this famous physicist. But even though he revolutionized our understanding of time and space, many people who are outside of like specifically physics and science and maybe philosophy are not all well aware of exactly what his ideas were. And so we're going to try and get to that basic understanding. What he did overall was move us away from the Newtonian conception of time and space to this relativistic conception of time and space. According to Newton, time and space were two separate things. They were each independent of each other. So in the old Newtonian paradigm, no matter how fast or how slow an object is moving through space in terms of its velocity, that would have no impact at all on the rate of time passing. So according to like Newton and everybody before Einstein, it was thought that no matter what an object is doing in terms of its velocity through space and movement, that would remain completely unrelated to the passage of time. That time just is a sort of linear passage from past, present, and into the future, and the rate that it passes cannot possibly be affected by anything else. But Einstein showed us that in fact that's not true, that time and space are linked, that they're inextricably woven together into one fabric, which is just called space-time. And once you understand this concept of space-time, you start to notice that the way that objects move and the velocity that they move at relative to other objects in space actually does change the time frame in which time passes relative to that object. And so there are very far-reaching and even puzzling and bizarre even implications of these theories that we're going to try and wrap our minds around. So let's just get into it then. Here's what Einstein starts off by mentioning. He says, suppose that lightning strikes the rails on an embankment of like a train track at 2 points that are distant from each other. So imagine that this is like a railway track. Like a train will travel along this track. And there are 2 points on it. Here's point A, and here's point B. Suppose that there are 2 lightning bolts that strike at those 2 points, A and B, okay? Now, he says something that sounds deceptively simple. He says, I want you to now imagine that these 2 lightning strikes that happen at A and B, I want you to just assume that they occur simultaneously, that they happen simultaneously. Now, this is when Einstein starts to kind of clue the reader in that there's something a little bit difficult about explaining what that means. He says, let's suppose they happen simultaneously. And your first instinct is going to be like, sure, okay, no problem, done. They happen simultaneously, I can imagine that. But now he has a little bit of a trickier question. He says, can you tell me, what does it exactly mean, though, that they happen simultaneously? Like, what is the definition of simultaneous? What is the definition of simultaneous events? And the thing that's difficult about the question here is that try to answer that. And it's very hard to answer it without saying some phrase which is circular for the terms same time as, right? So like, can you tell me what 2 events happening simultaneously means in other words? And try your best not to just say something that amounts to, they happen simultaneously or at the same time. Any idea? There's a way of getting to the explanation. Einstein will provide it, but he plays with the reader a little at the beginning by saying, try your best to give a definition of simultaneous, and you'll realize it's not so easy as it seems at first, because any attempt to state it runs up against this circularity that you're going to just sort of grasp for some definition which says ultimately simultaneous means that they happen at the same time. Any thoughts about that in our chat? If a person has never seen the word simultaneous, you're trying to tell them what it means, what would you tell that person? Anything? I mean, I'm just trying to give you a sense of the difficulty here. But what do you know? Let me hear in the chat if there's any commentary you have on this. Because this is the starting point for this lesson here. 2 lightning strikes occur, they happen simultaneously. Question, what does this mean? Question, what does it mean that they are simultaneous specifically? What can I deduce from the absence of comment? Does it mean that, okay, Cameron, could you say a specific time? So Cameron, you're thinking like they both happen at 12 or something? Like they both happen at exactly 12:01 and 32 seconds. Well, if you did say that, though, you would be saying, again, that related to a time indication of the clock, they both happen at the same time. But now it's like, if we don't have clocks, right, like just in the physical sense, what does it mean that they're happening at the same time? It just sounds as though you're saying, well, they do happen at the same time. So it's difficult. Look, I don't want to give you guys too much trouble with this. In a way, it kind of makes sense that you're having a troubling time giving any explanation, because even the genius Einstein says, yeah, it's not so easy to explain as it seems at first. And here's what he says. I'll read it to you, okay? So you can hear him say it. Don't take my word for it. Here's Einstein. So he says to you, lightning has struck the rails on the railway embankment at 2 places, A and B, far distant from each other. Let me get your quote comment, sorry, page. When 2 plus things happen in the same instance, yeah, I understand that that's the most natural way to try and explain it. But again, same instance sounds like same time, which is just elliptical for simultaneous. So we just keep going in a circle. Simultaneous means same time, means same instance, same moment. But yeah, here, I'll read on. He says, I make the additional assertion that these 2 lightning flashes occur simultaneously. If I ask you whether there is meaning to this statement, you will answer my question yes. Like he's saying, if I ask you, do you know what that means? Anybody will say, sure, I know what it means. But if I now approach you with a request to explain to me the sense of the statement in more detail, more precisely, you find after some consideration that the answer to this question is not so easy as it appears at first sight. So he says, then next. After some time, perhaps the following answer would occur to you. And now he's quoting a hypothetical person answering the question. Someone might say, the significance of the statement is clear by itself, and it needs no further explanation. Now, he says, I can't be satisfied with that as a scientist and as a physicist. He says a lot of people might just throw their hands up and be like, come on, I can't really explain it. It's just too puzzling of a definition to precisely pin down. But we all use the word, and nobody ever looks twice when someone else says, hey, those things happen simultaneously. Nobody's ever confused by the meaning of it. So since we use the word and we have a kind of unanalyzed understanding of it, isn't that good enough? Just knowing sort of how to use the word and having no difficulty common sense-wise understanding each other. And Einstein doesn't give you that. He says, no, I'm sorry. For a scientist, we might not even really have any meaning behind this word. It might be meaningless unless we can give a definition of it that is so clear and precise that on the basis of this definition, we could design a test to physically test whether the two events were simultaneous or not. And so he says, until we have the means by which to experiment and test for whether they were simultaneous, then we don't really have any defined understanding of the concept. And we may be using a word that actually has no meaning at all. So he says, I insist that we determine how to test the question, how to test the proposition that the two lightning strikes were simultaneous. And if we don't have the means by which to devise such a test, then this word might not actually have any clear understanding or meaning. And that's what he says. He says, I can't be satisfied with this answer because of the following reason. Suppose that as a result of ingenious considerations, an able meteorologist discovered that the lightning must always strike A and B simultaneously. Then we would be faced with the task of testing whether or not this theoretical result is in accordance with the reality. We encounter the same difficulty with all physical statements in which the conception simultaneous plays a part. Now here's a key quote. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled in an actual case. So we thus require a definition of simultaneity such that this definition supplies us with the method by means of which, in this case, we can decide by experiment whether or not both the lightning strokes occur simultaneously. As long as this requirement is not satisfied, as long as I don't know how to test the proposition, I allow myself to be deceived as a physicist, and of course the same applies if I'm not a physicist, when I imagine that I'm able to attach a meaning to the statement of simultaneity. And he says, I ask the reader, don't proceed further until you're fully convinced on this point. Okay, so he says, I want you to understand that we cannot basically allow ourselves to have like a hand-waving, ambiguous, vague definition of simultaneity. Even if we think we understand it on an everyday, informal level, he says, unless we do have the detailed enough understanding by which we could test this, then we may be just talking about a term that doesn't really have any meaning at the end of the day. So let's try and find out how to test then whether the two lightning strikes happen simultaneously. And here he says is the test. Okay, so you ready? He says this is the test that we're going to perform to verify the question of their being simultaneous or not. So here's the idea. Let's measure the distance between point A and point B. Okay, and what that creates is a line segment AB. Okay, so A to B, call that a line. All right. Now, question. Is there a midpoint in between the 2 points A and B? What do you think? Anybody do geometry? Probably this is clear enough from any common sense point of view, but is there a midpoint that's intermediate between A and B? Sure, there is. Let's designate the midpoint here and call it M. And what is a midpoint? A midpoint is the point that bisects the line. So now there's an equidistance between A and M and B to M, right? Okay, so let's place an observer here at the exact midpoint between A and B. So this observer is standing off at the point M, and that means they're just as far away from A, they're an equal distance from A as they are from B, okay? Now here's another important point. We have to make sure that this observer who's at M is far back away enough from the railway that he can see A and B in one field of vision without having to like look left to right. Does that make sense to you? Why do you believe it's important that if this person here, this subject, is going to test for simultaneity of the two events, that he would have to be far back in space enough to see those in one field of vision? Why is that key? Why does it have to be so that like he's not so close, let's say, to A that he can only see that, and then he would have to like avert his eyes to another place to see the location of B? Why does it have to be that A and B will appear in one frame? Okay, so that he can see them both happening at once, right? If he was too close to one, right, and he saw lightning strike, and then quickly he just shifts his glance towards the other direction and he sees lightning strike there, in that case, would he have been able to verify that they were simultaneous? No, because there's a short interval of time, you see, between when he looked at the first thing and when he looked at the second. So even if he looks at lightning bolt A and sees the lightning illuminate and then quickly shifts his glance towards B and he sees that there's also lightning there, that would not be able to tell us enough information as to whether they were simultaneous or not, because having not been able to see them both at once in the same visual perception, it could have been that while he was looking at the first one, the second one had not happened yet, and it started to occur in the interim between him moving his head. So it's not so much that, distance does affect time, Anthony, and we will get to that, but just for him to be able to observe the two events to determine whether they're simultaneous or non-simultaneous, he does have to be far back enough. Or Einstein says, here's another option. If he's too close, then he must be outfitted with refracted mirrors at 90-degree angles, so that through the use of the mirrors, he could see the two events by having the mirrors placed in such a way that they would locate those events and make it visible to his eyes. Okay, so just first of all I've said is we've got these two lightning strikes, correct? There's a midpoint between them. Okay, here's this observer who's going to stand still. He's motionless at midpoint M, and he's far back away enough from A and B to see those two things happening in one field of vision. Okay, now here's the point. If the two lightning strikes emitted from A and B reach him at point M, and he sees the two events occur at the same moment from the specific midpoint M, then relative to the observer here, we would say that they were simultaneous. But there's a couple of little extra things that have to be mentioned. We have to stipulate that the speed of light is constant, so that the speed of light moving from A to M is the same velocity as the speed of light moving from B to M. Okay, so if the speed of light is the same from these 2 points to M, then receiving the two light signals at M in the same moment would indicate that they emitted from their two respective origin points at the same time. But if the speed of light was variable, and if it was non-uniform, like so say the speed of light from A to M was faster than the light from B to M, then this observer at the midpoint would not be able to verify that they were simultaneous. So, for example, suppose that the light ray that moves from A to M was twice as fast as the light ray that moves from B to M, okay? Now, if the incoming light from A is 2 times faster than the incoming light from B, then if they reached him at the same time, which one left first? If they both arrive at M at the same time, but one of the two light rays is twice as speedy, though they have arrived at the same time, did they depart at the same time? That's my question. It's like two objects that have velocity, these photons. If this photon is twice as fast as this one, but they arrive at M at the same moment, then which one departed first? Correct, Anthony. B would have departed first in that case, because since it is twice as slow, it would have needed twice as much time to reach M. So basically in that case, B emits the photon, and since it's twice as slow, it gets halfway through its journey, and then A emits the photon, and since it's twice as fast, it catches up, and they both arrive at the finish line at the same point in time. So we can't have that. We can't have this assumption that light moves at variable speeds. If so, then having this observer at the midpoint, even though it's equidistant between the two signals, we could not infer from them arriving at M at the same point that they departed from their origins at the same moment. So we just therefore stipulate that the speed of light is fixed. So the velocity from B to M is the same velocity as from a to m. So this velocity v is equal to this velocity v. Under those conditions, if we stipulate that the speed of light is fixed and constant, we can arrive at our definition of simultaneity now. Let's ask a quick question about how vision even works physically, okay? Because it's not magic. How is it that you're able to see the screen that you're looking at right now? Like, what's the physical explanation of that? Can anyone give me it really quick? What's the science of vision? How is it that you're capable of even viewing the lecture that you're watching on a screen right now? What happens? What happens that provides you with this visual information that allows you to see it? Do you know the story behind that physically? Maybe I can get you to understand it, even if you're not 100% clear about it. If you close your eyes right now, can you see this lecture? That's an easy one. Let me know. With eyes closed, is the lecture visible? No, it's not. Okay, good. Well, why not? How come? What's the physical reason why not? What happens when you close your eyes that makes you unable to see the things in the environment? Why does that produce the result you can't see something? What's the reason of that? No light, exactly. Because when the eyes are closed, you have like the skin of your eyelids that blocks incoming light from entering the eye. And so when the light can't come in, you can't derive visual information from the objects that the light reflects off of. Okay, so how does vision work? Photons of light bounce off of the object that you see, and then those light rays travel to your eye at the speed of light, and the visual information is processed by your brain, and then you just see the object. But of course, if you place a barrier between the light rays and your eye itself, like by closing the eyes or by having shades or whatever, then the light cannot reach you, okay? And you won't see the object. Now, it's not magic then. You're seeing things because light is reflected off of objects at some distance away from you, and then the incoming photons are received by your retina. Now, the speed of light is a finite speed, and we actually know exactly what it is due to the experimental results of James Clerk Maxwell and others in the 19th and 20th century. So we know exactly that the speed of light is a definite speed. It's 186,000 miles per second. So in every 1 second interval, the photon will travel exactly 186,000 miles. And it's a constant speed. The speed of light is the same speed for all photons traveling anywhere in space. It's also the maximum physical speed. Nothing can travel faster than that. So if the speed of light is the same from A to M as it is from B to M, and if this person is equally distant from A and B, then just think of the sort of math equation here. He receives the light signals at the same moment, they've traveled the same distance, and they're moving at the same speed. So if these two photons have traveled the same distance at the same speed, and we have those two factors held fixed, then we can infer that they must have emitted from their respective origin points at the same time. Thus, they are simultaneous. Okay? So let me read more of his words on this and just connect it to what we've said. So he says, after thinking the matter over for some time, you then offer the following suggestion with which to test simultaneity. By measuring along the rails, the connecting line A to B should be measured up, and an observer placed at the midpoint M of the distance AB. This observer should be supplied with an arrangement, for example, two mirrors inclined at 90 degrees, which allows him visually to observe both places A and B in the same visual field. Now, if the observer perceives the two flashes of lightning at the same time from that point M, then they are simultaneous relative to him. He says, I am very pleased with this suggestion, but for all that, I cannot regard the matter as quite settled because I feel constrained to raise the following objection. The definition would certainly be right, but only if I know that the light by means of which an observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. And he says, well, that my definition satisfies this demand is indisputable, that light requires the same time to traverse the path A to M as for the path B to M is neither a supposition nor a hypothesis, but a stipulation which I make to arrive at the definition of simultaneity. But with that stipulated that light is fixed and constant in terms of its rate of travel, we've got our definition here. Okay, and so this therefore defines for us what simultaneity is in a sense. It just means that if two light signals received from an observer arrive to his visual system at the same moment, then relative to that observer, we would say that they happen simultaneously. And this then gives us a new way of thinking about how clocks coordinate objects in time and space. Like when say you have an appointment to be at the doctor at 9 a.m. on Friday. One way to think about that is that the pointer hands of the clock, which is just a reliable measuring instrument, they should show the clock face coordinates of 9, and that should be viewed in simultaneity with the event of you entering the doctor's office. So like you should be able to observe all coordinated clocks showing that time on the clock face, and that event will be witnessed by your eyes as simultaneous with you entering the lobby of the office. So we can assign 2 events to be simultaneous relative to this definition when the 2 light signals arrive to the visual system of an observer placed midway between the 2 events. But it gets very weird and trippy now. We haven't even gotten to the weird part yet. The weird part is when you start to see that based on this analysis, simultaneous event is relative. That the same 2 events which are simultaneous with respect to this man are not simultaneous with respect to a second man who has a different state of motion. Okay, so let me go ahead then and add a second observer to our scenario here. Okay, so let's consider a variation on the example, and this is going to reveal to you that simultaneity is not absolute, that it's just relative. So now I want you to imagine that we have this train, and the train is traveling along the railway from the direction of A towards B, okay? And let's suppose this train is traveling with a constant velocity v. There's an observer position on the train that's moving from left to right. Okay, now, every moving object where there's every case where there is an observer provides us with a different frame of reference. If the observer is in motion, then his frame of reference is relative to the body which is in motion. So, you know, like from the standpoint of the guy who's in the moving train, he views all objects relative to the velocity of the moving train. To the observer who's standing motionless off to the side, he views all events relative to his motionless frame of reference. You know, so the moving train is one reference frame, and the motionless observer here is a different one. So every event on the embankment also corresponds to a particular point on the train. Now ask yourself, are 2 events which are simultaneous with reference to this observer also simultaneous relative to this observer who is on the train? And Einstein shows us no. Let me explain. So when we said that these 2 lightning strikes were simultaneous with respect to this observer, we meant that the light rays emitted from A and B meet at the midpoint M of the length A to B at the same moment. But A and B also are events that correspond to positions seen from the moving train. So let M prime be the midpoint between A and B as it is observed from the perspective of the person who's on the moving train with velocity v. Okay, so all I've said here is that there's a line which just we can assign the midpoint and call it M for this observer, and the same position in space which bisects A and B, we'll call it M prime as seen from the second observer who's got velocity. Now, I want you to imagine this, that as this guy's traveling on the train with velocity v, he intersects with the midpoint at the exact moment that this person conducts his observation of the 2 events and sees them happening simultaneously. Okay? So if we had like a video playback of the whole sequence of events, there's 2 observers on the scene. One in the train, one standing off motionless at M. If we pause the playthrough of the video at the split second when he is aligned at this point, they would both be standing at the midpoint, except he's being carried with velocity v towards the right. Okay? But for like one very brief instant, he's at the same midpoint that he is at while he's conducting his observation, and he sees these things happening simultaneously at that point in time. But now here's my question to you, and see if you can put these pieces together in your mind. Will the second observer on the moving train see A and B happening simultaneously if he does his observation at the moment that he surpasses M prime? So he's in a constant state of velocity. He's not resting or pausing as he goes through the scene, as he sweeps through A and B. While he's passing at that velocity, he conducts his observation as he hits point M prime. Will he see A and B happening simultaneously the same way that he did, yes or no? That's my question. Well, the second guy on the train who's passing through the midpoint at the exact moment the second person is doing his observation at the motionless embankment position, will he also see them happening simultaneously, yes or no? Just a question. You need to tell me, though, what you think. Don't be scared. It's just science. What do you think? Will the second observer, okay, good, Anthony, no, but you have a question mark, so I know you're kind of like tentative about saying that, but there's a very, very clear reason why, and we'll get to it. Why do you think that though this man sees the two events happening simultaneously and he's standing still, big hint, standing still, no, Eva, the answer is no. He's standing still at M, he sees events A and B happening simultaneously. This guy's not standing still. He's got velocity V, and he is traveling in the direction of B. He intersects with the midpoint while he does this observation, but as he conducts that same observation, he sees one event happen before the other, and therefore they are happening out of sequence. They're not in sync. Which of the two events is going to be seen as happening first, according to the second observer who's passing through the midpoint? Let's get this question answered. Which of the two, A or B, is the one that will be seen first by our moving observer who's sliding to the right? Who's sliding to the right as they bypass the midpoint? Which of the two events will be seen first? Good, Jason, it is B. It is exactly B that is the right answer. But tell me, why is that the right answer? Why is it that although the other guy sees them happening at the same time, moving man sees B first, before A? Tell me what's the reason for that. That's the correct answer, so you have the correct intuition, and I'm sure you have a thought behind it. Why is it that he sees B happening instead of A first? Okay, because some of the train's velocity can cancel some of the light's velocity. That's a different way of putting it that I'm usually heard, but sort of, yes. I think the most easy way to state that same information is that he has velocity V, right? And so he creates an asymmetrical distance between himself and the two light signals, correct? He is getting closer onto the event B. He's moving closer to it, so it's an unequal distance. There's an equal distance for A and B to travel to reach this guy, because he stands still and he just waits at midpoint M. But while this person passes through the midpoint, he's rushing away from A and towards B. Since the speed of light is constant, a moving target with a visual perception system that cannot possibly receive the two light signals at the same time if he's running closer to one than the other, he's going to be hit by the photons from B quicker than the ones from A, because A has farther to travel since he's going to bypass the midpoint as it's rushing towards him, and the velocity of the light from B will reach him sooner because there's less distance for it to travel. So if he's closer to B than he is to A, then this light signal has to play a little catch up to get to him, and this one will get to him faster. So let me read to you the same explanation given here by Einstein. He says, are two events which are simultaneous with reference to the railway embankment also simultaneous relative to the train? We shall show directly that the answer is no. When we say that the lightning strikes A and B are simultaneous with respect to the embankment, we mean the rays of light emitted at places A and B where the lightning occurs meet each other at the midpoint M of the length AB of the embankment. But the events A and B are also corresponding to positions A and B on the train. Let M prime be the midpoint of the distance A to B on the traveling train. Now, just when the flashes of lightning occur, M prime coincides with M. But as he continues traveling, he moves towards the right in the diagram with the velocity V of the train that's carrying his body. So if he was sitting in position M prime and the train possessed no velocity, then he would remain permanently at that midpoint and the light rays emitted by the flashes of A and B would reach him simultaneously. But in reality, he is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Hence, the observer will see the beam of light emitted from B earlier than he will see the beam of light emitted from A. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B took place earlier than the lightning flash A. And that is the important result. The result is that events which are simultaneous with reference to the embankment are not simultaneous with reference to the train, and vice versa. So every reference body has its own particular time. Unless we are told the reference body to which the statement of time refers, there is no meaning in a statement of the time of an event. Before the advent of the theory of relativity, it had always been tacitly assumed that that in physics, that the statement of time had an absolute meaning, that it was independent of the state of motion of the body of reference. But now we have just seen that this assumption is incompatible with the most natural definition of simultaneous. So that is the final word. To repeat, there's two different states of motion when it comes to these two observers. Observer number one remains at rest, situated at the midpoint M. And if he sees the two events happening simultaneously, then we regard them as simultaneous relative to him because we have these factors held fixed. The light signals have traveled an equal distance. They're moving at the same velocity. So if they arrive to M and he sees them at once, that means they've covered the same distance at the same velocity. Therefore, they must have been departing from their origins at the same time. Okay, it's kind of like if you have two runners and they're both competing in a 5K and they both leave from the starting line at this, well, let me get that, repeat that. There's two runners, they move at exact same velocity. There's a set course, which is the same distance for both. If they arrive at the finish line at the same time and they've been moving the exact same velocity the whole way, then they must have left at the same time. But this guy is a different individual. He's moving through the scene with velocity v. As he traverses the midpoint, he briefly coincides with the position of the motionless observer standing at M. But since he's not frozen and he continues just this constant travel from left to right, he bypasses the midpoint, thus creating a smaller interval of space between his vision system and B and a greater interval of space between his vision system and A. So unlike this person, the light signals have an asymmetric distance to travel. A has to go farther than B does. And therefore, since the speed of light is the same, they won't reach him at the same time. So he's going to see B as happening first and then A happening second. Now, here's an important point to clarify. Whenever I teach this stuff on Einstein, some students almost have, I think, like intellectual resistance to the result. Like, so some people will take this wrong interpretation that really they are simultaneous and he sees it as it is. And the second guy who's traveling just sees like some kind of distortion of the facts or some illusion that's produced by his state of motion. So like in fact they're simultaneous, but if you're moving around like this guy, you see an illusion where it seems like they're not. That's not the correct explanation. The correct analysis is that there's no fact about whether they're objectively simultaneous. It's just absolutely relative. Because neither of these two people have the correct standpoint from which to observe the two events. It's not like because he's motionless, he has the objective viewer's standpoint. And since he's in motion, his viewpoint is just some distortion of reality. Because you need to understand that every observer who is in this universe is always in motion relative to something. Like you're on the surface of the planet Earth, which by itself is traveling at a high rate of velocity at all times, even when you seem to be like sitting still like you think you are right now. So there's no leverage point from which we can say this observer has the real objective condition of observation, and the other one is somehow positioned in a way that will give them a false interpretation of the facts. So we can no more say that these two events are simultaneous objectively than we can say that B happens and then A. And if you want to make it even trippier and weirder, think about if we had a third observer on the scene, okay? On a second train that's traveling in the opposite direction. Okay? If this guy moving in the opposite direction passes through the midpoint M double prime, and he does so while this guy's aligned with him and this guy is aligned with him, but he's traveling in the opposite direction, which of the two lightning strikes will be seen first by our third observer? In his condition of observation, for the same reasons, in parallel, but just going the opposite direction, he will see which event first. This new observer I've added to the scenario. Yeah, he would see A happen first and then B, because as he's traveling in the direction of A and away from B, the light signals emitted from A have a shorter distance, unlike B, which has a longer distance. So, Megan, can you quickly repeat how A has to travel farther if the strikes occur when the guy moving reaches M and M prime is equidistant from A and B? Because he's moving. He's moving. He doesn't sit still at M prime. He's in a train. This train just continues to travel. So even if this guy stands still and A and B can reach him at the same time, relative to the second observer, since he's moving away from A, the observer who sees them happening simultaneously will have them reach him at the same time. But in the case of the second observer, he's further away from A by the time the light signal reaches him, and he's closer to B. So it just has to do with his state of motion relative to the two observed events. He's getting closer to B, further from A, And so when they're both traveling at 186,000 miles per second, an object that's closer to something that's moving 186,000 per second is going to receive that information faster than when he's moving farther from it. So yeah, M prime and M are aligned in space, but for two observers, he's moving past it while he's standing still at it. And that's the difference. It's good, Megan. But what I was just trying to say in the end here, and I'm closing for now, we'll wrap it up and recap at the beginning on Friday. We have 3 different conditions of observation and 3 different answers. Is A and B simultaneous? Well, relative to one possible observer. Does B happen first? Yes, relative to another observer. Does A happen first? Yes, also relative to a third observer. And now it looks like the sequence of events in time and space is getting all jumbled up. Concerning A and B, we cannot say any fact about which one happens first or even whether they're at the same time. And that starts to really, when you think about it in a bigger picture, when you stop thinking just about the lightning bolts of this one throwaway example, it's very, very unsettling because it sort of means that there's no objective linear sequence to any of the events in time and space. Like you think this thing is happening before, you know, the final exam, and the final exam is happening before you graduate Chapman, and these things happen in a linear order. They can't be reconfigured into a different order. But what this shows us is that at least according to some possible observer in space and time, the ordering of events could be reconfigured, and there's no objective fact about the priority of the things happening in past, present, and future. If that is true, that's very strange, because it means that the things that you think of today as being like out in the future, not having happened yet, no fact about them, that they are objectively real, that they do exist, and it's just the illusion of your condition of observation that makes it seem like they have not happened yet. If that is true, it spills over into all kinds of wild consequences for free will and metaphysics. Like, if everything in the future is predetermined because all the events in space-time objectively exist, then there's no way that you can affect the future course of events. They're predetermined, they're destined to happen, and if that's the case, then I just have to wish everyone good luck, because you're going to need good luck. But anyway, then, let's just continue with this on Friday. There's more to say about the time and space stuff, but it's some of the most interesting material, I think, and it really connects to physics. So anyway, guys, have a great day. Like I said, I am almost done with those midterms. They will be done this week. Through the weekend, you'll be able to check on your grades. So great. Thanks again, everyone. Have a great day. I guess I've held you just a minute longer, but take care and stay safe from the fires and everything else. I'll see you guys soon. Okay, bye-bye.